Hello everyone, and today I will be showing you how to graph the titration curve of a titration between a weak acid and a strong base. And in this case, the weak acid will be hydrofluoric acid and the strong base will be NaOH. I'd like to shout out Mrs. Busen, my great chemistry teacher. She actually gave me this problem. And to start out, we're going to be looking at what point, or the original pH of this hydrofluoric acid solution. Okay, so we're going to be dealing with this equation, the hydrofluoric acid, to turn into the hydrogen ions and fluoride ions. And so we're going to set up an ice chart. And the original molarity of hydrofluoric acid is going to be 0.05. And we don't have either of these. So minus X plus X. And since the pKa, I'll write here. Since the Ka, is equal to 7.2 times 10 to the negative 4th, it's so small that we don't have to add in the negative minus X right here. Okay, so we're going to set up the equation. And that's going to be equal to the pKa. And X will be equal to, X is going to be, in this case, the equilibrium concentration of hydrofluoric, or of the hydrogen ions. So that's going to be equal to 0.006 molarity, and then you're going to negative log that. To get the original pH to be equal to 2.22. And if we bring back our curve, then we can plot that point already. So it's going to be about, it's not going to be completely accurate, but it'll be about there. So now we have our first point. Okay, now our second point is the second thing we have to do is we have to find out where the equivalence point is going to occur, and that's going to be where the moles of the acid, or H plus, is going to be equal to the moles of the hydroxide. And so we have, if we do our molar equation, or molarity equation for our hydrofluoric acid, we'll have 0.01 over N for moles equal to 0.05. Moles is going to be equal to 5 times 10 to the negative 4. And so we're going to have that many moles over X to find liters. We're going to use it's going to be the exact same moles in this. So we're going to find the, we're going to set it up to equal to 0.020 molarity of the NaOH. And so this is going to be liters, in liters, and then so you solve, and X is going to be equal to 0.025 liters of NaOH you need, which is also equal to 25 milliliters. So if we come back to our graph, we know that at this point, it's going to be our equivalence point. So it'll be about a straight line there. Okay. Now another trick we could do for this is the pKa is going to be at the half equivalence point. The pKa is going to be equal to the pH. So at 12.5, right here, the pKa is to the negative log 7.2 times 10 to the negative 4. And that is actually equal to 3.14. So that will go right there. All right, so now we have two dots because we have the pKa, which is half of 25 is 12.5. Then negative log, or the negative log the Ka, and we get our point. All right, now we're gonna have to find the, now we will find the pH at the equivalence point. Okay, so to do this is actually pretty tricky. So since we know the moles are gonna be equal of the, so we're gonna set up our net equation. Okay, so we're gonna do this ice chart in moles actually, just because it's easier. So 5e to the negative 4. I'm just using e instead of writing time 10 to the negative. So it's a different way to write scientific notation. So we're gonna have 0 of that, 0 of that, and there's no limiting reagent, so both of these will end up being 0 at the end. And this doesn't really matter, but we're gonna add 5e to the negative 4. So 5e to the negative 4. So that's gonna be the moles. And if you put that over the total at the equivalent, the total volume, which is gonna be 25 milliliters plus 10, it's gonna be 0.035 liters. See if we add these two. And then that's going to give us a concentration equal to 0.0143 molarity. All right. Now the next step is we're going to have to do another ice chart, and I'll actually do that ice chart down here. Okay, so I drew this equation out, and so we're going to have this whole equation, and it's going to be the fluorine, and this is how we're going to find the pH. And so we're going to have, this is the initial concentration that we got from here. We're going to have 0, 0, and then add the x's. So the equation is going to be x squared over, and we got to remember, since this is a basic equation with the F minus, so we're going to have to do equal to 1 negative 14, we're going to have to turn our pKa value up here into a pKb value. So we're going to put 7.2 e to negative 4. And so then you can just solve that for x. And that's actually, but we're solving for x is going to be the concentration of OH minus, all right? And so the concentration of OH minus is going to be 4.46 times 10 to the negative 7. And if we negative log that, the POH will be equal to 6.35. And then we're going to subtract that by from 14 to be equal to 7.65 for the actual pH at the point of equivalence. So now we can graph that point, 7.65. So at the equivalence point 25, 7.65 out there. All right, now we actually only need about 2 more points just to make it completely exact. So we can start to draw. But we're gonna find a point at 20 and at 30 just to make it give us our good curve. Okay, so to do this equation, we're gonna deal in moles yet again. And so at 20 milliliters added of NaOH, we're still gonna have an initial concentration of this many moles of hydrophilic acid, but we're also gonna have 4 moles of hydroxide. And we're using hydroxide because NaOH, it's a strong acid, so it completely dissociates. And so the amount of moles of NaOH we're going to have is going to be equal to the amount of moles of Na and of OH minus. So this doesn't matter. We're going to have 0 of that. since this is, we're going to have excess of that because that's the excess reagent. So limiting reagent. Zero of that. And this is all in moles, we have to remember. And for these equations, we can use the Henderson-Hasselbalch equation. And so we can do negative log 7.2 times 10 to the negative 4 plus the log. And now we got to remember, we got to turn these values back into values of molarity because these are in moles. And so the total volume right now is going to be 30 milliliters. And so if we put that over 0.03, both these values, and we put our, this value is going to be equal to 0.0133, and this value is going to be equal to 0.00333, and then this will give us a pH that will be equal to 3.74. All right, so that's going to be another point we can graph. We bring our paper back over. 3.74 at 20 milliliters added. Oh, it's not too big of a jump. We could go like that. And like that. Now we're going to have our 30 milliliters. Okay, so now our last one is we're going to look at, find the pH at 30 milliliters of NaOH added. And if we bring our equation back, always going to have 5 of these moles. But this time, the OH we're going to have is 6 e to the negative 4. And this doesn't matter, and we get 0 of that. And so we're going to subtract 5. Okay, so then we're going to have 0 of that. We're going to have 1 molar of that. And 5 e to the negative 4 of that. But this doesn't really matter because we're just focusing on the pH, so we're going to have OH already. Okay, so the concentration of the OH minus is going to be equal to 0.0025. And so therefore, if we negative log that, POH is going to equal 2.6. And if we subtract that by 14 minus 2.6, the pH is going to be equal to 11.40. Okay, so if we bring back our graph at 30, so we're going to be at 11.40 out here. All right, so we can graph it like that, and we're going to see a nice titration curve. We're not really sure, but now we know how to graph that. All right, thanks everybody for watching.